Hey, so today I'm going to be making a video on logic using truth tables and understanding what necessary and sufficiency is with logic. So when we think about logic or any logical situation, it's what it sounds like in math and in basic English. So let's say uh, one thing happens, another should happen. Uh, if my mom went to the store, she got food. So let's type that out, and we're gonna break this down and look at each part of it. So if my mom went to the store, then she got food. So this right here is an if-then statement. So this part, the if my mom went to the store, is the if, and trying to find the right brush to use, but so this part is the if. So this is called the predicate. So it is saying that if this part of the statement has to be true for the conclusion to be true. So this is called the predicate of a statement, an if-then statement, and this is the conclusion. And so we generally say that this statement is true if the predicate is true and the conclusion is true. Well, what happens if my mom didn't go to the store? If it's false, then either way, the logic is going to hold because the predicate wasn't satisfied. So it doesn't matter if the conclusion is satisfied or not because the statement still holds. So what you have to think of as is it's a statement saying if P then Q, which is denoted like this with the arrow. So this is really a statement. And you can kind of see over here, I'm foreshadowing. There's a lot of stuff we can do with the predicate and the conclusion. But if the predicate now is false, then no matter the value of the conclusion, so if the conclusion's false, if my mom didn't go to the store and then she didn't get food, then that holds because either way, the predicate is false, so the value of the conclusion doesn't matter, the statement. So let's put false here for the predicate and true here. Now, this is an equation like I've just shown you above. So this is really where the truth table comes in. We're getting all these values, and based on these values coupled together, so T to T, truth to truth, false to false, false to truth, we get one value for P to Q. So here, when both values are true, it's true for an if-then statement. When the predicate is false, the if-then statement is always true. So for both of these, it's true. Now, what happens if the predicate is true, but the conclusion is false? Well, what happens here is this is basically saying um, the opposite of our statement. It's saying that if my mom went to the store, then she didn't get food. That's not true because we're saying that if she did go, she did get food. So this is false. So whenever the predicate is true, but the conclusion is false, it is always false. This is a general rule for any if then statement. So now we have our grid over here, which if you're ever using truth tables, you always want to grid. It makes it so much easier. So we label general values for P and Q. Since there's four possible values of true, false, there's two, either true or false, and there's four spots, there's four combinations for the predicate and the conclusion. It doesn't matter in which order you write them. I like to go true, true, false, and then true, true, false, false. So we know that if both the predicate and conclusion are true, then P then Q is true. Now, so this is everything we did over here. So if the predicate is false, it's always true. Since the predicate is true here, but the conclusion is false, it's false. If both are false, then it's also true, obviously. Now, what happens when we have some statement P and Q? So that means that both the predicate and conclusion have to be true. So if my mom went to the store and she got food, then that's satisfied by this statement because it's true, because she got food because she went to the store, and both things happened because of the predicate. The conclusion happened because of the predicate. Both are true. So P and Q is true. Now, what happens if, and again, we're looking at P and Q. This P then Q is not necessary defining P and Q. We're just looking purely at P and Q. Now, if one's false and one's true, or the predicate is false and the conclusion is true, or the predicate is true and the conclusion is false, these are both going to be false because they both have to be true. That is the only way for this to be satisfied. Now, what if we have P or Q? So that's saying that one of the two has to be true. So that's saying either my mom went to the store or she got food. So if both are true, then that means this one is true. Now, if uh, she didn't go to the store, but she did get food, then this is true because one of the two events happened. So essentially, treat the predicate as an event A and the conclusion as an event B, and it'll make it a lot easier to think of almost because it's more of an equation rather than a logical statement. Now, what happens if she did go to the store but she didn't get food? Well, one of the two is true. Now, what if she didn't do both? Then neither happened, so it's false. Now, here, what happens if we say, is it true or false if the opposite of P happens, then Q happens? So what we want to do here, this is more confusing logically because it's saying if my mom didn't go to the store, then she got food. It's almost a backwards kind of statement. So what you want to do here is you want to really utilize your logic table. This is where this makes it a lot easier because all we can do is you reverse this. So since it's binary, either true or false, one of two values, um, we make each value here the opposite. So if this is true in the first row right here, P becomes false. So we have false then true. We know that's a true because when the predicate is false, it's always true. Now we have a false here and a true here. If we reverse this, we get true, true. That makes two trues, which makes it true. And then if we have a true here, now this becomes a false, and we false, false, which we know is true. Now, what do we have here? We have false, false. This false becomes a true, and then we're left with a false because it's a true and a false. So now, if we want to kind of go back and we want to look at these true, false values and say, okay, does this hold for our statement? This can kind of we can use this to go back and using these truth tables figure out if these statements are equivalent. So for example, if you get some row like let's say P or Q right here, P or Q and negative P then Q. So I'm talking about if excluding these two rows, if this is row A, B, C, and D. Row C and D, for each value of P and Q, they have the same values. What does that mean? It means that because of this, these statements are logically equivalent. And that means that for any value of the predicate or the conclusion, we can say that these values will always be the same and that they mean essentially the same thing logically. Logically equivalent. That is the term for it. You're not exactly saying the same thing, but in terms of logic, you are. Now, a very small thing on top of this, but very important, is necessary and sufficiency. So, in this statement, we say, if my mom went to the store, then she got food. So, uh, is going to the store necessary to getting food? Well, I'm saying if my mom went to the store, then she got food. But I'm not saying that there's not any other way that she could have gotten food. She could have ordered it online and gotten food. It doesn't mean that just because we have food. Basically, I'm saying if Q is true, the conclusion, it does not mean that P must have happened. You see what I'm doing here? This is a key understanding. If you reverse the two, so if you're saying, let's say the conclusion is true, then does P have to be true? No, not in this case, because it is not a necessary condition. So your mom did not have to go to the store to get food. However, is it sufficient? Well, sufficient is saying if the predicate did happen, then Q must have happened. So it's saying if my mom went to the store, um, did she get food? And yes, that's what we're seeing right here. If we know that the predicate is true, if we know for sure that the value of the predicate is true and she went to the store, then we know for sure that she got food. So what can we say from this? We can say that going to store is a sufficient condition to getting food, but it is not necessary. So let me type that out because it's kind of confusing. So uh, based off of our if then statement, um, our mom going to the store is a sufficient but non but not necessary condition for getting food. That is how it is worded. So essentially, sufficiency deals with if P then Q. Q is only true if P is true. It is not looking at any of these P then Q, P and Q, P or Q. It is looking at P then Q. So, um, w- w- but for something that is necessary, we're looking at if Q then P. If Q has to be true for P to be true. Because what does the arrow mean? The arrow means if. So it's if then. So when we reverse the two, what we're looking at is we're basically saying if we know that the conclusion happened, then that means that predicate had to have happened. But in our logic statement that we already have, the words we have, if my mom went to the store, then she got food, we know that isn't true just based off of logic and other things that could have happened. So that's what necessary and sufficiency is. So this is a pretty actually it's a pretty sizable breakdown of this concept, and it's very useful even considering basic statements. I might make a video looking at a statement and then breaking down the truth values into actual words. So putting the predicate in terms of if my mom went to the store, the conclusion, then she got food, and seeing if all these statements are logically equivalent. And it can get much more complicated than this, because what happens if you have something like um, uh, P or Q and negative P then Q, or P and Q, and it's just um, one giant logical statement. Then you have to use a bunch of different tools and it compounds and everything like that. But it is a very useful tool. Um, I hope you enjoyed, and I hope you learned, and I hope you know more about logic using truth tables now. Thanks.